Good evening, my name is Prithvisha Nath. I am the TA for this course of Vibration of Continuous System. I am a PhD student in the Department of Aerospace Engineering at IIT Madras. This is the week 2 for this course and we will solve some questions. So this is the first question. Here we need to find the natural frequency for the double pendulum. So in this question, it consists of two point masses M1 and M2 suspended by strings of length L1 and L2, and the masses are considered to have only horizontal motion. So the masses are considered to have only horizontal motion. Let θ1 and θ2 be the angles that the string make at any instant of time. With the vertical, and let x1 and x2 be the horizontal displacement of the masses. So here we assume that the system has small amplitudes. So for small amplitude, what we do is we considered sine theta almost equal to theta. So the expression for this would be what will be sine theta 1? From this image we can see that sine theta 1 will be x1 by L1. Now since the amplitude is small, we can write sine theta 1 as theta 1. So theta 1 is equals to x1 by L1. Now similarly for sine theta 2, what we can write is x2 by x1 by L2. Similarly for sine theta 2 also we can write it as theta 2 since it is small amplitude. Now let us make the free body diagram for the masses. So here is the free body diagram for the two masses. So what will be the equation? Here we consider that there is no motion in the vertical direction. So the vertical components of the force balance each other. So what can we write from this free body diagram? So as we can see from the image, this image, T2 cos theta 2 is equals to M2G So considering no motion in the vertical direction, the vertical component of the force must balance. So we can write this as T2 cos theta 2 equals to M2G. Similarly for the mass M1 we can write it as T1 cos theta 1 equals to M1G plus T2 cos theta 2. Now since we assume that theta 1 and theta 2 are small, so we can write this expressions as follows. The first expression becomes T2 equals to M2G, and T1, the second expression becomes T1 equals M1G plus T2. So So as you can see, the above relations become like this. Now I substitute M2G in place of T2. So what is the equation that it becomes? M1G plus M2G, that is equals to M1 plus M2 into G. Now we write the differential equation for the two masses in the horizontal direction. Now what can we write from this figure? From this figure what can we write? M1 x1 double dot equals T2 sin theta 2 minus T1 sin theta 1. So the differential equation for the two masses are M1 x1 double dot equals T2 sin theta 2 minus T1 sin theta 1. Similarly, for the second mass, what the equation should be? M2 x2 double dot equals what should it be? Minus T2 sin theta 2. Now we substitute the equation for T1 and T2, and similarly for sin theta 1 and theta 2 in the differential equation. So these are the equation we get. M1, now we substitute the value. Values for T1, T2, sin theta 1 and sin theta 2. So what my equation becomes is M1 x1 double dot in place of T2 what do we write? M2G, and in place of T1 we write minus M1 plus M2 into G sin theta 1. Now in place of sin theta 1 we write this expression. Sin theta 1 becomes theta 1 x1 by L1. So sin theta 2 also becomes x2 minus x1. Okay, I'm writing this again. So T2 m1 x1 double dot becomes t2 x2 minus x1 by L2 from this expression sin theta 2, from the expression of sin theta 2, minus T1 x1 by L1. Now substituting the value for T1 and T2, it becomes M2G x2 minus x1 by L2 minus M1 plus M2 L1 into G x1, which is equal to M1 x1 double dot. Now we need to rearrange this equation. So M2G x2 by L2 minus M2 into G x1 divided by L2 minus M1G x1 by L1 minus M2G x1 by L1 equals to M1 x1 double dot. Now this expression I can write it as plus M2G x1 by L2 equals M2G x2 divided by L2. Now finally rearranging this equation, we can write it as now this is for the first mass. This equation is for the first mass. Now we write similarly the equation for the second mass. Now for the second mass the equation is minus T2 x2 minus x1 divided by L2 that is equals to M2 x2 double dot. Now in place of T2 I substitute M2G, so this becomes minus M2G x2 minus x1 divided by L2. Now similarly rearranging this equation, we can write this as now this is for the second mass. Now we can assume x1 to be capital X1 sin omega t and x2 assuming x1 to be capital X1 sin omega t and small x2 to be capital X2 sin omega t. So we substitute this in the above equation. We substitute the value of x1 and x2 in the equations that we got just now. So final equation which we get is this. So first we substitute this minus m1 omega square So first what we get, what is x1 double dot from this equation? It is x1. First we need to find x1 double dot. So what is x1 dot? x1 cos omega t into omega, x2 dot becomes omega x2 cos omega t. Therefore x1 double dot becomes omega square x1 sin omega t with a minus, and x2 double dot becomes omega square x2 sin omega t with minus. Now substituting this in the equation, in place of m1 x1 double dot, what we substitute is, what we get is minus of m1 omega square plus m1 plus m2 divided by L1 plus m2 by L2 whole multiplied by G x1 equals to m2 L2 G into x2. Similarly, for the second equation, what we get is minus m2 omega square plus m2 gl2 into x2 divided by m2 equals to m2 l2 gx1. Now we can write this as x in terms of x1 by x2. So from the first equation, what we get, this is from the first equation we can write x1 by x2 as m2 L2 into G divided by this entire expression on the left hand side. So this becomes minus of m1 omega square. So this is one of the equation. Now from second equation also we'll get similar x1 by x2. So from the second equation what we get is Now similarly from the second equation, what we can write is x1 by x2 equals so from the second equation, what we get is x1 by x2 equals m2g divided by L2 minus m2 omega square divided by m2 by L2 into g. So if we equate these two equations, we get the frequency, that is the value for the omega. So equating these two equations, omega can be value for omega is obtained, which is the frequency. Now suppose if the masses m1 and m2 are equal, so in that case what is the situation? And L1, L2 is also equal, that is equal to some value L. So what is the value for omega that we get? So let us compute that. Let us consider m1 equals m2 equals m and L2 equals L1 equals L. So in the above equation, if we simply substitute the value for m2 and m1 as m and L2 and L1 as L, what we get? We get this as x1 by x2. From the first equation we get m by L into g. Now the denominator becomes 2m by L minus m omega square. So this becomes m by L into g 3m by L into g minus m omega square. So what can I write this as? G by L 3g by L minus omega square. Similarly, from the second expression of x1 by x2, that is this equation, what we get? x1 by x2 equals minus m omega square plus mg divided by L divided by mg by L. So what does that become? G by L minus omega square divided by G by L. Now we need to equate the above two equation so that we can calculate the value of omega. So equating the value, now equating 7 and 8. What we can write it? G by L divided by 3G by L minus omega square equals G by L minus omega square divided by G by L. So if we expand this becomes so rearranging the equation, it becomes like this: omega to the power 4 omega square G plus 2G square by L square equals to 0. Now finally this equation becomes, so if we divide it by G square, this equation becomes like this. Now this is my final equation. From this equation we get the value of omega 1 and omega 2. So solving for omega, we get omega 1 as G by L 2 minus root 2, and omega 2 is G by L 2 plus root 2. So these are the natural frequency of the double pendulum. So moving on to the next problem, it says a U-tube open to atmosphere at both ends contain a column of length L of certain liquid. Find the natural period of oscillation of the liquid column. So as it can be seen, it is a U-tube and it has a liquid column of length L, and we are asked to find the natural period of oscillation. So how can we solve this question? At any instant, let the liquid column be displaced from the equilibrium position by this length x, as it can be seen from the image. Now, okay, so at any instant, let the liquid column be displaced from the equilibrium position through a distance x. Let rho be the density, the mass density, and A be the cross-sectional area of the tube. So what is the kinetic energy for this column? It is half into mass into velocity square. So how can we write the mass of the liquid? So I can write the mass of the liquid as follows. Density into volume. So density we already know as rho. And what is the volume? Volume is A into L. So what is the kinetic energy for the liquid column? It is half into mass, that is rho AL into x dot squared. X dot is the velocity of the liquid column. Similarly, how can I write the potential energy? Potential energy can be written as rho into A into x into g into x. So what is the total energy for the system? Total energy of the system is kinetic energy plus potential energy, and that remains constant. The total energy of the system remains constant. So the total energy of the system is potential energy plus kinetic energy, that is equals to rho A x g into x into half rho al x dot whole square, that is equals to constant. Now we differentiate this equation with respect to time. So how can I write this equation as? We can write this as half into L x dot plus gx equals 0. Now again we can rearrange the equation. We can rearrange the equation writing it as we can write this equation as x double dot equals to 2g by L into x equals 0. Now then, what is my omega? Omega is square root of this term 2g by L. So we can write omega equals 2g by L, which is the natural frequency of the system. Similarly, how can we find the time period? Time period is given by 2 pi by omega. So this becomes as 2 pi root over of L by 2g. So this is the final answer for this question. Now, moving on to the next problem. Find the natural frequency of vibration of the half solid cylinder when it is slightly displaced from the equilibrium position and released. So we can see that there is a half solid cylinder and it is said that it is slightly displaced from its equilibrium position, and we are asked to find the natural frequency of vibration. So what we have to do in this question is, so it's displaced by the angle theta. So what is this distance OG? OG can be found out to be 4r by 3 pi. Now we can write IO as IG plus M x bar whole square. Here I is the mass moment inertia of this solid cylinder. So how can we write Ig as? Ig can be written as IO minus mx bar whole square. Here m is the mass of the solid cylinder. Capital M is the mass of the half solid cylinder. Now we have to substitute the values for Ig and IO. So IO is m r square by 2, and here r is the radius. R equals the radius of the half solid cylinder. So in place of IO, I write mr square by 2, and in place of x bar, I substitute so this I can write it as minus, this becomes 16 by 9 pi square. Now when the system is displaced from the equilibrium position, how can I write the potential energy and the kinetic energy? The kinetic energy is simply half I omega square, that is omega, and omega is d theta by dt. So in the displaced position at any instant of time, the energies of the system are, kinetic energy is half IP omega square. Here omega is d theta by dt, and similarly the potential energy can be written as mg x bar 1 minus cos theta. Because the system is displaced by this amount, initially the theta was 0. So how much is it displaced? It is displaced by this much height. So the h is h minus total displacement is x bar minus x bar cos theta. So taking common, I can write it as mg x bar 1 minus cos theta. Therefore, the total energy of the system is constant. So I write this as, I substitute the value of potential and kinetic energy. So this becomes mg x bar we know as 4r by 3 pi into 1 minus cos theta plus half ip theta dot square. Theta dot here is d theta by dt. So this is constant. Now what we have to do is differentiate this with respect to time. Now what I do? Differentiating one with respect to time. So how can I write this term as? I can write this as mg 4r by 3 pi sin theta d theta by dt plus ip d theta by dt into d square theta dt square equals 0. Now cancelling the common terms, the equation becomes now mg 4r by 3 pi sin theta plus ip d square theta by dt square equals 0. Now since sin theta is small, we can write sin theta as theta. So ip theta double dot plus mg by 4r 3 pi theta equals 0. Now here theta double dot is so we can write this equation as three pi taking ip to dividing by ip, we get this as this. Now from here, how what is the omega? Omega is simply the this term mg into 4r divided by 3 pi into ip. Now we got the omega in terms of this term, but we have to calculate the value of ip. So how can we do that? Now from this figure we can see that Gp equals to OP minus of OG. So we can write this as GP equals to OP minus OG. This can be written for small amplitudes of vibration. For small amplitudes of vibration. Now, what is IP? IP is Ig plus M into Gp square. From the figure you can see that IP can be written as Ig plus M into Gp square. So IP equals Ig plus M into Gp square. Now I write OP minus OG in place of Gp. So the equation becomes now I can substitute OP and OG. So how can I write this? We already know the value of Ig. What is Ig? Oh, sorry, this is Ig. So in place of Ig, we will write I'm going to substitute this in place of Ig. That is mr square half minus 16 by 9 pi square. Now in place of OP, OP is what? OP is simply the radius of this solid cylinder. OP, as you can see, is the radius of the solid cylinder. So I write R in place of OP, and OG is 4R by 3 pi. Now I need to simplify this. IP equals, I'm taking mr square as common, so half minus 16 9 pi square plus 16 9 pi square minus 8 3 pi. So these two terms get cancelled. So finally, what is the expression for IP? mr square equal mr square into 3 by 2 minus 8 by 3 pi. Now finally what I need to do is substitute this value of IP in the expression for omega. So substituting the value for IP. What was my omega? Omega is mg4r divided by 3 pi into IP. So what is my omega? Omega is capital M 4r divided by 3 3 pi into IP. Now I just substitute IP. So what is the equation? What is the final equation? This becomes 6 pi 9 pi minus 16. So pi gets cancelled, 3 gets cancelled with 6. So the final expression becomes, and I can cancel m and r. So the final expression becomes 8g divided by 9 pi minus 16 divided by r. So this is the final expression for omega. So what we did in this problem is, first we know this distance OG, that is 4r by 3 pi. Now from the parallel axis theorem, we know that IO can be written as IG plus M into x bar square. So rearranging it in terms of IG, we can write it as IO minus M x bar square. So we know IO is mr square divided by 2, and we simply substitute x bar as 4r by 3 pi. So solving it, we get IG. Now it is said that this is displaced slightly from its equilibrium position. So we can write the kinetic energy as half Ip into omega square, and omega is d theta by dt. So potential energy also can be written as mg x bar minus into 1 minus cos theta. So we know that the total energy of the system remains constant. So the total energy is potential energy plus the kinetic energy. Now we simply substitute the values for potential energy and kinetic energy as this one. Now we differentiate this equation with respect to time. So the right hand side of the equation becomes 0 since it's constant. So the first term can be written as this, mg mg into 4r by 3 pi into sine theta d theta by dt, plus the second term can be written as ip. The 2 gets cancelled here, of course, with the half. So ip into d theta dt into d square theta by dt square. So now we finally get this in terms of mg4r divided by 3 pi into sine theta plus ip d square theta dt square equals 0. So now what I do is simply rearrange this equation in terms of theta double dot. So I take the ip in the denominator. So this is my omega in terms of ip. But we need to find the value of ip. How can we calculate that? For calculating ip, we need the value of gp. Gp can be seen to be OP minus OG from this figure. Gp can be written as OP minus OG, and this is of course for small displacement, small amplitudes. So IP, again using the parallel axis theorem, IP can be written as IG plus M into GP square. Now I simply substitute OP minus OG in place of GP. Now what is OP? OP is, from this figure we can see OP is the radius. Now I'll just write it here. OP is R, and OG we have already seen it to be 4R by 3 pi. Now we simply substitute IG. At the beginning of the sum we calculated IG, as you can see from here. So mr square into half minus 16 by 9 pi square. So we substitute here. Then in place of OP we substitute R and then OG. Now just expanding this and taking mr square common, we get this expression for IP. So my IP becomes mr square into 3 by 2 minus of 8 by 3 pi. Now finally what I do is I substitute IP in this expression for omega. So after simplifying this, omega comes out to be 8G divided by R 9 pi minus 16 under root of 8G. Under root of this whole expression. Now the next problem. A 3-degree freedom system is shown. This is a 3 degrees of freedom system, as you can see from the figure. What we have to do is write down its differential equation of motion by using Newton's second law. And finally what we need to do is put it in matrix form. So first what I need to do is draw the free body diagram. So for the first body, the spring force is acting towards the left. So this can be written as on the right hand side, it can be written as K x2 minus x1. Similarly, for the second mass, we can write this as, this should act in opposite direction. So on the right, we can write this as K into x3 minus x2. Similarly, for the third mass, only the force is acting towards left. So K into x3 minus x2. Now what we need to do is write the equation for the three masses. So first, for the first mass, how can we write the equation? So for the first mass, the equation is like this: K x2 minus x1 minus of 3k x1, since it is acting in the opposite direction, equals mass into acceleration. So what is the mass of this body? The mass of this body is 4m. So 4m into x1 double dot. Now what I do is I rearrange this expression. So this can be written as kx2 minus kx1 minus 3kx1 equals 4m x1 double dot. So kx2 minus 4k x1 equals 4m x1 double dot. So finally, after rearranging, how can I write this? 4m x1 double dot plus 4k x1 minus kx2 equals 0. So this is the first equation. Similarly, what can I write for the second mass? The mass for the second body is 2m. So from the free body diagram, I can see that it should be written as minus k of x2 minus x1 plus k. This should be minus because it is acting towards left. And kx3 minus x2 is acting towards the right, as you can see from the free body diagram. So k x3 minus x2 equals mass into acceleration. The mass is 2m. So 2m x2 double dot. Now I expand it and rearrange it. So minus of kx2 plus kx1 plus kx3 minus kx2 equals 2m x2 double dot. So this becomes 2m x2 double dot minus kx1 plus 2kx2 minus kx3 equals 0. So this is the second equation. Now similarly we have to do the same thing for the third mass. So on the third mass, as we can see, a force acts only towards the left. So we write it as minus k x3 minus x2 equals m x3 double dot. So I rearrange this equation as minus kx3 plus kx2 equals mx3 double dot. So mx3 double dot plus minus kx2 plus kx3 equals 0. So this is the third equation. Now what does the question say? We have to write down the differential equation and put this equation in form of a matrix. So how do we do that? First I am writing down the three equations. So what were my three equations? 4mx1 double dot plus 4kx1 minus kx2 equals 0. The second equation was 2mx2 double dot minus kx1 plus 2kx2 minus kx3 equals 0. And the third equation is mx3 double dot plus kx3 minus kx2 equals 0. So first taking the coefficients for x1, x2 and x3 double dot. So how can I write this as? So 4m 0 0 0 2m 0 0 0 m you can multiply and see if the first terms are coming. So if I multiply this 4m into x1 square, the first term is coming into 0 and 0, so that becomes 0. For the second row, 0 into x1 double square, that is 0, plus 2m into x2 double dot, that is 2m x2 double dot, and plus 0 into x3 double dot, so that is also 0. So what is left? Only 2m x double dot. So the second equation is also coming. For the third equation, we can see it is like 0 into x1 double dot plus 0 into x2 double dot plus m into x3 double dot. So the third equation is also coming. Now how can I write the second part? Plus for what is the coefficient of x1? It is 4k. The coefficient of x2 is minus k. So this is 4k. This is minus k. And there is no coefficient for x3, so that is 0. Similarly, for the second equation, we see that the coefficient for x1 is minus k. Similarly, for x2 it is 2k, and for x3 it is minus k. Now moving on to the last equation, what is the coefficient for x1 and x2? x1 do not have any coefficient, so I write it as 0. x2 is minus k, so I write minus k, and x3 is plus k. So here I simply write x1, x2 and x3. And what is the right hand side of the equation? It is just 0. So I write it like this, equals 0, 0, 0. So the mass matrix is, so what is the mass matrix? It is, we have written down, see, 4m 0 0 0 2m 0 0 0 m. So the mass matrix is 4m 0 0 0 2m 0 0 0 m. And similarly, what is the stiffness matrix? It is, we got it as 4k minus k 0 minus k 2k minus k 0 minus k k. So the stiffness matrix becomes 4k minus k 0 minus k 2k minus k 0 minus k k. So I can write this like this. So what did we do in this question? We had to write down the equation of motion, write down the differential equation of motion for this system by using Newton's second law and put it in form of a matrix. So first what we did is we simply first drew the free body diagram. For the first mass, the spring force is acting towards the left. It's acting on both sides. So on the left it is acting 3k x1 and on right it is k into x2 minus x1. Similarly for the second mass, it is on the left side it is acting as k into x2 minus x1 and on the right side it is k x3 minus x2. And similarly for the third mass, only the force is acting towards the left, that is k into x3 minus x2. Now what do? I put this in form of three equations. So considering the first mass, for the first mass, it is written as first we write the first force that is acting towards the right, that is kx2 minus x1, then minus of 3kx1 that is acting towards left, so the minus equals to mass into acceleration. So the mass for the first mass is 4m into the acceleration is x1 double dot. Now we rearrange it and finally get it as 4m x1 double dot plus 4k x1 minus kx2 equals 0. This is for the first mass. Now for the second mass. Now going to the free body diagram, we can see that a force of kx2 minus x1 is acting towards left, so it should be taken. It should be written as minus of that since it's acting towards the left, and then kx3 minus x2 that is acting towards the right, so plus kx3 minus x2 equals 2m x2 double dot 2m because the mass is 2m. Now rearranging it, we finally get it as 2m x2 double dot minus of kx1 plus 2kx2 minus kx3 equals 0. So this was for the second mass. Now for the third mass, this equation is for the third mass. Going to the free body diagram, we see that only the force is acting towards the left on the third mass. So the equation is written as minus of kx3 minus x2 equals mx3 double dot. For the third body, the mass is m, only m. So rearranging the equation, what we get, mx3 double dot minus of kx2 plus kx3 equals 0. Now I finally write these equations for masses 1, 2 and 3, and then I write the coefficients for x1 double dot. In the first equation, there is no term for x2, x3. X2 double dot, x3 double dot. There is only coefficient for x1 double dot. So I write 4m and rest 2 are 0. For the second equation, the coefficient for x2 double dot is 2m, and the other two coefficients, that is for x1 and x3 double dot, it is 0. So I put 0 in those places. And from the third equation we can see that the coefficient for x3 double dot is m, and for rest other two it's 0. Similarly, for the stiffness matrix, we see that the coefficient of x1 is 4k and x2 is minus k, but there is no coefficient for x3, so we write a 0 in that place. Similarly, from the second equation, the coefficient for x2 is minus k. The coefficient of x1 is minus k, the coefficient of x2 is 2k, and the coefficient of x3 is minus k. And lastly, for the last equation, the coefficient of x1 is 0, x2 is minus k, and x3 is k. So this is my M matrix. This is the M matrix. This is the K matrix. And as it is seen, the right hand side is 0. So I write it like this. So for the first term, what we did? For the first sum, a double pendulum was given, for which there were two masses, m1 and m2. Each were suspended by strings of length L1 and L2 respectively. So these masses were considered to have motion only in the horizontal direction. So it was in and there was no motion in the vertical direction. So, and θ1 and θ2 were the angles made by the string with the vertical, and x1 and x2 were the horizontal displacement of the masses. So from this, what is sin θ1? Sin θ1 can, for the first mass, sin θ1 can be written as x1 by L1. Now since we have considered for small amplitude, this is the assumption for small amplitude. For small amplitude. Similarly, what sin θ2 can be written as x2 minus x1 divided by L2, and that is approximated to θ2 since it is small amplitude. Now I construct the free body diagrams. So tension T1 is acting up in this direction, and tension 2 is acting on the in the downward direction, as it can be seen. Similarly for mass M2, this can be seen. Now what I do, I write the force balance, because we have considered there is no motion in the vertical direction. So the masses should remain in the masses should not have any acceleration. So I can write it as T2 cos θ2. In the vertical direction, T2 cos θ2 is balanced by M2 into G, as it can be seen from the free body diagram. Similarly for mass M1, the component of T1 cos θ1 is balanced by M1G plus T2 cos θ2. Now since we have assumed θ1 and θ2 to be small, I can write T2 as m2g, and T1 as m1g plus T2. Now what we do? Now we write the differential equation for the masses in the horizontal direction. This is in the horizontal direction. We assume that the masses are moving in the horizontal direction. So for the first mass, it is like T2 sine theta 2. It can be seen from here, T2 sine theta 2 minus of T1 sine theta 1 equals to m1 into acceleration. Similarly for the second mass, T2 sine theta 2 minus of T2 sine theta 2, since it's acting towards left, gives the mass into acceleration. Now what I do is substitute the values for T1, T2, sine theta 1 and sine theta 2. Now what was sine theta 2? It was x2 minus x1 by L2, and theta 1 was x1 by L1. Now what I do is substitute for T2 and T1. T2 is m2g by L2, and T1 is m1 plus m2 into g divided by L1 equals m1 x1 double dot. Now what I do, I simply rearrange. So this becomes like this: m2g x2 into L2 minus m2g x1 by L2 minus of m1g x1 by L1 minus of m2g x1 by L1 equals to m1 x1 double dot. Now simply we rearrange this. This becomes m1 x1 double dot plus m1 plus m2 divided by L1 into g into x1. We are just taking it on the right hand side. Then plus m2g x1 L2, and this term we are keeping it on the left hand side itself. So m2g x2 L2 divided by L2. So finally my equation becomes like this. Similarly, for the second equation, what we do, we substitute the values of T2 and then T2 sine theta 2. Sine theta 2 was x2 minus x1 divided by L2 equals m2 x2 double dot, and T2 was m2 into g. So the second equation is like this. Now we assume that x1 equals to capital X1 into sine omega t, x2 equals to capital X2 sine omega t. Now if we differentiate it, once we get it as omega x1 cos omega t, x2 equals to omega x2 cos omega t. Now since we require acceleration of the system, we differentiate once again. That becomes x1 double dot becomes minus of omega square x1 sine omega t and minus of omega square x2 sine omega t. Now we just substituting the values. What we get, this was the first equation. Now in place of x1 double dot, I substitute this expression. So it becomes minus m1 omega square plus m1 plus m2 L1 plus m2 divided by L2 whole into g and x1 remains. The common terms get cancelled. So m2 divided by L2 into G into x2. Now the second equation, this equation we have substituted the values for x, and what we got is minus m2 omega square plus m2 divided by L2g into x2 equals m2 divided by L2g into x1. So we just rearrange this these two equations. From the first equation we get this from equation 3. This is from equation 3. From equation 3. This we get from equation 3. And this is from equation 4. Now we simply solve these to obtain the value for omega. Now we have considered a special case where m1 and m2 are same, that is equals to m, and L2 equals L1, that is equals to L. Now we simply substitute in the equation that we got. Like in this equation number 5 we substitute and get this value, and from equation number 6 we get equation 8. Now from 7 and 8 we can just rearrange. Since these two terms are equal, since this ratio x1 by x2 are equal, we can write it like this. So this came out like this: GL by GL whole square equals GL minus omega square into 3GL by omega square. So I just rearrange the terms, and finally what I get is omega to the power 4 g square minus 4 omega square Lg plus 2 divided by L square equals 0. Now when I solve for omega, I get these two values, that is, as you can see from here. Now for the second question, what we did was we considered an U tube which had both ends open to the atmosphere, and it had a column of liquid of length L. So we were asked to find the natural period of the oscillation. So at any instant we assume that the liquid is displaced from the equilibrium position through a distance x, as you can see from the figure. Now rho is the mass density and A is the area of the cross-sectional area of the tube. So from here we see that mass can be written as density into volume. So density is rho and volume is A into L. So from here the kinetic energy is half mv square. So in place of m I substitute rho Al, and v is x dot whole square. Now potential energy can be written as rho Ax g into x. So the total energy of the system is potential energy plus kinetic energy, and it remains constant for the system. So I have written down the potential and the kinetic energy. Now what I do is differentiate it with respect to time. After differentiating it, I get the expression like this. So now I rearrange the equation. And omega is under root of 2g by L. Similarly, time period is 2 pi by omega. So I substitute the value of omega and got the time period like this. Similarly, for this sum also, we had to find the frequency. Here also we differentiated the total energy with respect to time, and we got the omega. So these were the problems that we solved for week 2.